Here I have a magnet suspended from some string, which allows it to swing like a pendulum. And I also have this block of copper, which doesn't attract the magnet because copper isn't magnetic. But watch what happens when I swing the magnet above the copper. This happens because the magnet induces electric currents in the copper, and those currents generate their own magnetic field that fights back and slow it down. And the magnet's kinetic energy is converted into heat inside of the copper. But what if instead of wasting that energy as heat, could we capture it to power something? This video is sponsored by SolidWorks. More on them later. I spent a bit of time building this small scale prototype, where there's some magnets on the end of an arm that's suspended by some low friction bearings, and this allows it to swing just like a pendulum. But I've replaced the block of copper with some copper wire that's wound into a coil, which currently doesn't do anything because the ends of the wire are disconnected. Why don't we connect a small LED to it to see if we can power it? So the LED does blink for a very short period of time as the magnets pass the coil, but it only seems to do it when the magnets pass from right to left. And I think that's because it's generating alternating current within the coil, and the LED requires direct current. To fix this, I can use some diodes, which are basically one-way valves for electricity, and arrange them into what's called a full bridge rectifier, which converts the alternating current into direct current. And this also means I can add a capacitor to store energy between each swing. How cool is that? Right, now we should scale up this thing and see what else we can power. Fortunately, I already have a large triangular frame from an old trebuchet project, which makes for the perfect pendulum test platform. And I have some leftover aluminium box section to make a new arm for the pendulum. But why even try to extract energy from a pendulum in the first place? Well, a pendulum is a form of mechanical energy storage. As with low friction bearings, the arm can be raised and maintain a constant swing until friction slows it down. And with the strong frame, it's very easy to add lots of weight to the pendulum to store more energy. Then to charge the pendulum, I simply raise the weight and let go, which in this case will happily swing for over an hour. And we can build a generator to convert the stored energy into usable electrical energy. In a generator, there are many magnets mounted with alternating pole directions, and both sides have the same magnetic strength, but we only care about the side facing the coil. By adding small magnets in between the big ones, rotated in specific directions, we can create what's called a Hall-back array, which boosts the magnetic field on one side and weakens it on the other. We can boost this even further by adding an iron plate behind the magnets, as iron gives the magnetic field an easier path to loop back around, which helps concentrate even more of it on one side, hopefully generating more power in the coil. So for the backplate, I've got this sheet of mild steel, which is about 99% iron, but I've never machined steel on my homemade CNC mill. So I grabbed a new carbide end mill, chose some recommended feeds and speeds, and hit the emergency stop button. It seems my spindle just doesn't have enough torque at the lower RPMs required for steel. So I reduced the depth of cut and it was cutting much better. And we now have a mild steel backplate for the Hall-back array. I then 3D printed a plate that would hold the magnets at the perfect spacing for the generator, so I compressed in the magnets to the printed slots. And once complete, it was time to check if I had successfully built a Hall-back array. So on the backside, the magnetic field was still there, but it was very weak. In fact, it was barely noticeable. Whereas on the front side, it was incredibly strong. Which is great news because removing these magnets wouldn't be easy. So now the magnet plates can be mounted to the end of the pendulum arm, and I used some aluminium extrusions to create a platform underneath for the coils to mount to. To wind the coils, I first 3D printed a template out of clear resin on the Formlabs Form 4, which I can then wind some 0.4mm enamelled copper wire around to create a coil. I then printed this bridge looking structure that will attach to the platform under the pendulum. With my projects, I often show the build process, but very rarely show the design process, which is actually a huge portion of the work involved. And in order to turn an idea into an actual real part, I use the sponsor of this video, SolidWorks. With SolidWorks Design, I'll sketch out my designs, build them into a full 3D model, and then use assemblies to check everything will actually fit together once it's made. And if I need to send a part off to be manufactured, I can create production-ready drawings so the parts are properly defined. SolidWorks also has real-time collaboration tools for sharing designs and ideas, which is essential for product development. And even though I design all of these projects by myself, I'm constantly switching from designing parts in my office and tweaking them later when I'm in the workshop. So to know that I'm always working on the latest design is really nice. So right now you can get 15% off SolidWorks Design Standard by using my coupon code TomStanton15 or by going to the link in the description down below. Thank you very much to SolidWorks for sponsoring this video, and now let's get back to the build. And the coils can simply bolt into position between the magnets. And with a small LED connected, it's working exactly like the small scale prototype, which I then connected a full bridge rectifier, some capacitors, and my voltmeter to see what voltage it was producing. So we're already generating 4 volts. It's slowly climbing. I assume it needs to charge the capacitors a bit. There we go, the LED's lighting up at 8 volts. With the generator working, I wound 5 more coils to increase the power, for a total of 6 coils. But then noticed there was a few millimeters of side-to-side flex in the pendulum due to its size. So to prevent any catastrophic collisions, I made these small bumper guides to keep the magnets central when passing the coils. And to test the braking force of these new coils, I connected all the wires together to produce a direct short. And in a single swing, the pendulum comes to a complete stop. I then hooked up an oscilloscope to see the voltage produced by the coils, and noticed a small issue. This is the alternating voltage produced by the generator, and you'll see each cycle of the wave isn't the same voltage. It gradually increases and then decreases. And this happens because a single coil produces about 15 volts, and as the magnets pass more of the coils, the voltage adds up until it's about 80 volts in the middle. I think the only way to solve this is to wire the coils in pairs and have each pair wired to its own full bridge rectifier. And luckily I've already ordered far too many diodes, which I can use to create 3 full bridge rectifiers using this prototype PCB board, which can be mounted next to the coils with a 3D printed bracket and soldered up. So now if I measure the output voltage with the oscilloscope, we can see the diodes are doing their job by keeping the voltage positive, but also that the voltage peaks are far more consistent at just over 30 volts. I then soldered a few large capacitors together in parallel to make a 50,000 microfarad capacitor bank, and I made 2 of these for a total of 100,000 microfarads, or 100 millifarads, to store as much energy as possible between each swing of the pendulum. And now the pendulum generator is essentially finished, so let's re-add the weights and see what we can power with it. Right, so let's start with just one LED because we know this works, and let's make sure everything is still working now that the pendulum's finished. It takes a little while for the capacitors to charge up. Oh, it's getting brighter, it's getting brighter. Let's see if we can power more than just one. Here we go, 2 LEDs. Easily powering it. It's a bit dim, so let's push the pendulum a bit more. Let's try 3 LEDs. How about 4 LEDs? 5 LEDs? And finally, 6 LEDs. So as lighting up the LEDs seems pretty easy, let's try power some more things. Like how about an electric motor with a fan? Oh, wow. That's got loads of power. This fan really drains the energy from the pendulum, but I'll put it on the floor just to show you that I'm not powering it from a battery in my sleeve. How cool is that? Transferring motion to motion through electrical generation. So we now have a large pendulum that will store energy like a mechanical battery, and a generator to convert this stored energy into useful electricity. But how do we store more energy? The simple answer is to increase the gravitational potential energy at the start of the swing by raising the height of the weight. But this causes some issues. As a pendulum swings, the time to complete a full swing is constant and is defined by this formula. Essentially, the length of the arm is all that affects the swing period, and increasing the weight of the arm or its swing height doesn't change the time for a complete swing. However, this is only true if the angle of the pendulum swing is below about 10 to 15 degrees. If I increase the angle of the pendulum to the 12 o'clock position to maximise the stored energy, the time for each swing increases significantly, which would require a far larger capacitor bank for the generator to maintain a constant power output between the swings. Also, the voltage produced in the generator is directly proportional to the velocity of the pendulum at the bottom of its swing. So releasing the pendulum from higher results in a high initial voltage being generated. Then by the end of the swing, the voltage will be far lower. Therefore, I think the best way to store more energy is to just increase the weight and keep the height of the swing low. And this way the voltage and swing duration is far more consistent. And we can add a voltage regulator so the generator can run up to 30 volts and it can power the LEDs at a more comfortable 8 volts, which maintains a smooth power output for several minutes as it gradually converts the pendulum's energy into light. What's also interesting is the stored energy in the pendulum is directly proportional to the height of its swing, and we can measure the reduction in swing height to calculate the power consumption of the LEDs. So with the starting swing height of 18 centimeters above the center point, we can release the weight to power the LEDs, which after 3 minutes of swinging and therefore producing light, the pendulum swing has reduced by about 13 centimeters. Which for the 40 kilogram weight is equal to 51 joules. And because 1 watt is 1 joule per second, 51 joules over 180 seconds is an average power output of 0.28 of a watt. Which is quite low, but if I connect them to my variable power supply at the same voltage, it seems about right. I can even use a USB voltage regulator to charge my phone, though considering the maximum stored energy in the pendulum is only about 0.02 of a watt hour, I would need to raise the weight nearly 1,000 times to fully charge the battery. That's not 1,000 swings, that's raising the weight and letting it decelerate to a complete stop 1,000 times. Plus, the phone seems to discharge the capacitors too fast between each swing, resulting in an inconsistent charge rate, which the phone doesn't like. So how about we try powering something that requires a quick pulse of power, like this 400 kilovolt spark generator. Okay, spark generator in 3, 2, 1. Oh, that's just ridiculous. Or how about transferring the pendulum's swinging motion into linear motion using my homemade electromagnetic launcher? This launcher was previously used to launch a radio-controlled plane into the sky using magnets and electricity, and I must have stored it next to something metal as it's experienced some damage. But that shouldn't stop it from working, so with it hooked up to the pendulum generator, can we launch this paper plane? 3, 2, 1. Oh. So I think the pendulum doesn't generate enough power from a single swing. So I'm going to let the capacitors charge up and try again. Okay, the capacitors should be charged up now. So let's press the launch button in 3, 2, 1. Oh wow, that worked really well. So whilst the pendulum battery might have awful energy density compared to modern lithium batteries, it sure is fun to experiment with in the workshop. I hope you found this project interesting, and thank you very much for watching.